Hello, welcome to our first day of e-learning. We're going to start with the circle today. We're going to start by defining some of the elements of a circle. So if you remember when we constructed circles with our compasses at the beginning of the year, you start by putting your compass point down, and then you open your compass a fixed amount. And then you're able to keep that distance the same all the way around and make a circle. Well, that distance you open is called the radius, and the compass point is center. Now, another way to use the word radius, in addition to the distance that you keep your compass open, is it is a segment that goes from the center circle to a point on the circle. So all these down here figure are also called a radius, and the plural of that then would be radii. Now, our next definition is concentric circles, and concentric circles are two or more coplanar circles with the same center. So you guys are used to seeing those in a bullseye, right? Because these circles, if I had drawn them as actual circles, would have the same centers. All right. Third thing, two circles are congruent. They have congruent radii. So in order for them to match up point for point when you place them on top of each other, they need to have congruent radii. Next, we have the interior, exterior, and points on a circle. So a point is inside or in the interior of a circle if the distance from the center is less than the radius. So, for example, this would be a point on the interior. A point is outside or in the exterior of a circle if its distance from the center is greater than the radius. And finally, a point is on the circle if its distance from the center of the circle is equal to the radius. So point here would be on the circle. Now we have chords. Chords are segments that join any points on the circle. So if I have a point here on the circle and another point in the circle, if I join them together, they create a chord. Now, a diameter of a circle is a chord. So it has 2 points on the circle, but then it goes through the center. I didn't quite make it look right over here, but it has to go through the center and it has to have 2 points on the circle to be a diameter. So what do you think the longest chord in a circle is? If you said diameter, you are correct. All right. So a diameter is a chord. It's a special chord that passes through the center of the circle, and it also happens to be the longest chord in the circle. All right, now we've got some related theorems. Now we've got radii in a circle, and there are chords in a circle. It turns out that a radius is perpendicular to a chord, then it's going to end up bisecting the chord. Okay. And almost the converse of that theorem is true. There's a little caveat in there. If we go opposite way and we have a chord and we know the chord being bisected, well then, sorry, my touch screen working very well. It's going to be, if a radius of a chord bisects a chord, then it's going to be perpendicular to that chord. Now the caveat is that it can't be the diameter, because if it is the diameter, then any radius in a bisect it doesn't necessarily have to be perpendicular. That's why they have that extra that is not a diameter in the theorem. The third related theorem is that the perpendicular bisector of a chord passes through the center of a circle, because these other two theorems were talking about radii, and we know that radii have their input on the center. And so the perpendicular bisector of a chord, which is what all of these radii were in these other two theorems, they end in part of a perpendicular bisector. They have to go through the center of the circle. Okay. In the proofs I'm going to do for you, I just want to do a quick reminder about the perpendicular bisector theorems or the equidistance theorems. Remember we had like kites most of the time? Okay. And what happened was we segment, and then if the point was on that perpendicular bisector of segment, then any points on it equidistant from the endpoint. So this point up here would be equidistant, and this down here would be equidistant. Or we could go the opposite way and say if the point is equidistant from the endpoints, then this is the perpendicular bisector. All right. Last reminder from middle school, area of a circle is pi times radius squared, and circumference is pi times its diameter. Because diameter is equal to radii, sometimes we write this as circumference equals 2 pi r. Remember that the circumference is the perimeter of a circle. All right. So I'm going to do one of these proofs in here. Okay. The first one tells us that we're given circle Q, and that R is perpendicular to ST. Now we want to prove that PS is perpendicular to PT. I am going to start by using one of our new theorems that says that PR bisects ST. All right. So if PR bisects ST, the reason is because PR contains part of the radius, which would extend here, QR. It would go past QR. The radius actually would look like this. I should use a different color. The radius would actually be this, okay? But QR is a part of that. And that radius is also part of the line PR. Okay. So the reason is if a radius is perpendicular to a chord, then it bisects the chord. All right. And that means that PR is a perpendicular bisector of ST because I have its perpendicular and it bisects. So if perpendicular and bisects, then it's a perpendicular bisector. And now using my equidistance theorem, so remember I told you before these are powerful because they save us a lot of steps in proofs. I don't have to get these two triangles congruent. I can say PS is congruent to PT because if a point is on the perpendicular bisector of an element, and it is equidistant from the endpoints of the segment. All right. So we could have gone through congruent triangles, but this was a lot faster if you remember that equidistance theorem. All right. Next, we'll do a problem that uses this theorem. Okay, we're going to find the radius of a circle if a 60 centimeter chord is 16 centimeters from the center. All right, that means distance. Distance always measured along a perpendicular. All right, so I have a 60 centimeter chord. I have the fact that is 16 centimeters from the center. All right, and what we're going to do is we're going to add in a radius here. Now, I have a radius perpendicular to a chord. So that means that to bisect the chord, and that each of those segments are going to end up being 30. Now, these numbers should be familiar to you. We're looking for the radius here. Right? If you remember your Pythagorean triple, this means that we've got an 8, 15, 17 triangle that's been multiplied by 2. And so that means the missing side is 34. And so then that's going to be the radius for that circle. All right, we're going to do a similar type problem, a little different. Okay, so we've got another circle, and we've got a chord, and we're looking for the distance of the chord in the center of the circle. So these problems always kind of start like this. All right, and now I'm going to add in a radius here. And this time, I know that the radius is 13, and I know the length of the chord is 10. But if the length of the chord is 10, then because this other radius is perpendicular, each segment here is going to be 5. And now we're looking for the distance from the chord, and this is PQ, to the center. So that's, we're looking for this segment right here. And this should be familiar to you. This is a 5, 12, 13 triangle. And so then the missing distance is 12. Okay, then our last problem that we have to do is going to be the area and circumference review. So we want to find the exact value. And when it says exact value, we want to leave pi as part of our answer, because pi, as you know, is an irrational number. It goes on forever. And the minute you stop writing down the decimals, it's no longer exact. So we want to make sure we leave pi as part of our answer if I ask you for an exact value. We're going to find the area of a circle if a chord of length 48 is a distance of 7 from the center of the circle. All right, so we're going to start like we had done those other problems. All right, we've got a chord. Its length 48. And then we know that distance from the center is measured along perpendicular. So this is going to be 7. We know the chord here is 48. And in order to solve this problem, we're going to need to know what the radius is, because the area and circumference will both need to know the radius. All right, so if this was 48, this chord, we know a radius perpendicular to a chord is going to by a chord. So each of those are 24. I'm going to add in this radius here and be able to use Pythagorean theorem, but we don't actually need to use Pythagorean theorem because we know our triples. And hopefully you remember the 7, 24, 25 family. So that means that this radius here is 25. And so now it's pretty easy to find the area and the circumference. The area is equal to pi r squared. So that's going to be pi times 25 squared, which is 625 pi. And then the circumference is pi times diameter, or you can write that as 2 pi times r. So this will be 2 times pi times 25, and circumference will be 50 pi.